Right, everybody. I'm gonna go through section 9.4 on vectors. So a vector is a quantity that has both magnitude and direction. I like to think about vectors kind of as a ray. So it has a point kind of where it starts and it extends to another point. So it's kind of like, I guess, a line segment, but I say array because there's a certain direction that it goes. It doesn't just like exist there. It's like starting here and like shooting off that way. The magnitude is the size or extent of something. So in essence, for us, the length of the vector is our magnitude. So we know how to find lengths of things in math. The arrowhead indicates the direction. So again, there's a starting point and a place where it ends, and that is on purpose, and that is necessary. You might recall from geometry how we labeled rays. We took the starting point and a point that it went through and drew an arrow on top of it. But a geometric ray extends infinitely in one direction. And our vectors are not going to do that. Our vectors are going to have a set length. How we're going to label vectors, we are going to use kind of one letter most of the time. So again, the kind of difference here is that these are not going to be infinite. They're going to have a certain length that we have. A common way to represent vectors inside of vector brackets. So for instance, it's going to look like 2, 3, but instead of parentheses, it's going to have our pointed brackets. So it's going to look similar to an ordered pair. And it's actually going to help us kind of see where our vector is similar to an ordered pair. So a vector 2, 3 would be a vector starting from the origin going to the point 2, 3. And then we have this other notation that you'll see quite a bit with i's and j's. What I is it's the vector that goes directly to the right or to the left. So I is really the vector 1, 0. And j is the vector that takes our up and down stuff. Oops. So j would be our vector 0, 1. And we use I and j's to kind of, again, tell the directions. So I is kind of like our x direction, and j is kind of like our y direction. And if we think about our vector 2, 3, another way we can write this is our vector v equals 2i plus 3j. You'll see in like textbooks that the I and j will be bolded. Sometimes if you look in math or physics books, you'll see an I with a little thing on top of it called I hat and j hat. And I guess I wrote them right there. But normally you'll just see me writing I's and j's. If you like have our textbook, they're normally in bold. So vectors, we can add and subtract them. So I'm going to give you a sketch here. Let's say our vector v kind of looks like this. And let's say our vector w kind of looks like this. So if we were to do v plus w, we're going to start from the origin. We're going to go where v takes us. And then from the end of that vector, we go w. So let me sketch what that kind of looks like. So again, this is a sketch because v is going to kind of take us, that looks about how long I drew it. So we're going to do that first, and then we're going to go in the direction that w goes, and w kind of looks like that. So our vector v plus w is this one that I'm drawing in this pink color. This is the vector v plus w. So it's kind of like, it's not necessarily, I don't want to call it necessarily a triangle, but you go where the first vector takes you. From the end of that, you go where the second vector takes you. And from the very start to that ending place, that is our added vector. So we see that at the bottom here, we must position the vector so that the terminal ending point of the first vector coincides with the initial point, the start of the second. So those are some vector basics. We don't do a whole lot of adding and subtracting of vectors, I guess, graphically all the time. It's quite straightforward to do this algebraically. So we're going to take two vectors and have some numbers. So let's say our vector v equals 2i plus 3j. Another way we can write that is 2 comma 3 in our vector brackets. And we'll call w the vector 3i minus 4j. If we wrote it in vector brackets, that would be 3 comma minus 4. We're going to find v plus w and v minus w, but let me just draw a couple sketches here of what w and v would look like if we just drew them separately. So v, starting from the center of the origin, we would go 2 to the right, 3 up. That would be our ending point for our vector. There would be the vector v. The vector w, 3i minus 4j, that's 3 to the right, 4 down, 2, 3, 4. So that's what we're thinking of right now. So if we were to add them, we would take our vector w, kind of attach it to the end of v, and it's going to take us down here somewhere. If we were to subtract them, we'll see what happens with the numbers, so see if we can figure out how to graphically do this. So v plus w, you're just going to add the I components and j components. Let's see if I know how to spell. Separately. They don't really interact with each other when we're just adding and subtracting. So v plus w would be, you would take your 2i plus 3j, and you're adding 3i minus 4j. So we're just, it's kind of like terms almost. So 2i plus 3i, that would be 5i. 3j plus negative 4j is negative 1j. So write it like that, or we can write it kind of in our bracket notation, which would be 5 comma negative 1. Which kind of makes sense for this little spot of points that I drew, right? Go 5 right, down 1. Let's look at v minus w. 2i plus 3j minus 3i minus 4j. So 2i minus 3i, that is a negative I. 3i minus negative 4j, that's plus 7j. So where does that take us? That takes us way up here. So what we're doing to get these up here is we're going the opposite direction of w. So if you think about w here, flipping around, going the other way, that's where it's going to shoot us off to up there. So there's our vector v minus w, or we can write it in bracket notation as negative 1 comma 7 with our pointed brackets. We can add and subtract vectors. We can also multiply them by a scalar, by a number. So 3v, we're taking our same vectors as above. So if I were to do 3v, that's doing like 3 times 2i plus 3j. And it works the same way. We're going to multiply that 3, kind of distribute it to both components. So 6i plus 9j, or again in bracket notation, 6 comma 9, and then kind of putting everything together, 2v minus 3w. It's a little bit of work going on here. I'll write bracket notation through the work for this one. So 2 times 2 comma 3 minus 3 times 3 comma negative 4. So I'm going to take 2, multiply that into our first vector. So that would be 4 comma 6. I'll multiply the negative 3 and turn this into addition so I don't mess up on any signs. Negative 3 times 3 is negative 9. Negative 3 times negative 4 is 12. And again, add components. So we're going to take 4, add it to negative 9, get -5. 6 plus 12 is 18. So there's the vector in bracket notation. This time, if I go backwards, that would be -5i plus 18j. I like bracket notation, but both are used quite commonly. Magnitude, remember, magnitude was our length. So how, oops, I almost dropped my pen. How do we find the length of a vector? Well, first of all, let's talk about the symbol it uses. It almost looks like an absolute value, but it looks like an absolute value where we have double bars. That's going to be our symbol for the magnitude of a vector. It's just finding length. So how do we find a length? If you know your distance formula, this is distance formula. But since we always start from the center, 0, 0, I shouldn't say always, but since we mostly start from the center here, you know, your x2 minus x1, well, 1 of them is 0. So it's just like x squared and then plus y squared, and you take the square root of it. So this is really the distance formula, but here's our formula. Gonna have to know that the magnitude is going to be a squared plus b squared for our vector v equals a comma b. So looking at this vector right here with its terminal point at 3, 4, if we were going to find the magnitude of this vector, we would do the square root of 3 squared plus 4 squared. 9 plus 16 is 25. Square root of 25 is 5. So it's distance formula. It's not terribly challenging, but once it starts happening in terms of all this other stuff going on, that's where it starts getting a little confusing. Here on the next page, unit vectors. Unit, think about other stuff we've dealt with naming of units. Unit circle. Unit circle is called that because it had a radius 1. So a unit vector is going to be a vector in some direction, but it's going to have a magnitude, aka a length of 1. How can you find a unit vector based upon any vector you're given? You're going to take the vector itself and divide it by its length. That's going to always give you a vector that has a length of 1. We use u often to denote unit vectors, u for unit. So here's an example of how this works. If I wanted to find a unit vector in the same direction as 3i plus 4j, how does this work? We take our vector and we're going to divide it by its magnitude. So again, I'm going to write it in bracket notation. I'm a fan of that one. So I'm going to take the vector 3, 4, and I'm going to divide it by the magnitude of v, by its length. So I'm going to take 3 and divide it by some number. I'm going to take 4 and divide it by some number, and that's going to get us our unit vector. So what's the magnitude of v? We just did it on the previous page, but I'll do it again. That's the square root of 3 squared plus 4 squared, which will be 5. So putting that into our work, we're going to take our vector 3, 4, divide that by 5. So we're going to take 3 and divide it by 5, 4 and divide it by 5. So there is our unit vector in the same direction as v, 3/5, 4/5. That is a length of 1. We could also write that as, oops, I forgot the fraction, 3/5 I plus 4/5 j. Could write it in either way. At this point, try it with the second one. Put a pause on your video, see if that made sense. I'm going to start doing the work in a second, but you know, you should pause and try it yourself, see if you know what's going on. So first thing I'm going to do is actually draw a sketch of the vector. We'll call this our vector. So it's going to be 24. It's going to be 7 going this way. So this vector is going to be extra long. It's going to have a length of, if you think about your right triangles, of 25. What I really want for a unit vector is I want a vector that looks like that. It's going to have a length of 1. It's going to be a whole lot shorter, but it's going to go in the same direction. So how do we find that unit vector? We're going to take -724 and divide it by the magnitude of that vector. Now, I already said it out loud here, but I'll do the calculations anyway. We're going to take -7, square it. We're going to add that to 24 squared. That will be 25. That will be 25. So we're going to take -724, divide that by 25. So our unit vector will look like -7/25 or 24/25. And again, if you like the i's and j's, that would be -7/25 I plus 24/25 j. Vector going in the same direction has a very smaller length in this particular problem. All right, position vector is a vector between two ordered pairs. These are our vectors that don't just simply start at the origin. How we find the vector starting at some point x1, y1, going to the point x2, y2, is we just subtract. So we're going to subtract the point where you ended up from the point where, hold on one sec, my stuff is freezing. There we go. I got it back. So we would just take the ending coordinates x, y, and subtract them from the beginning coordinates. So as an example, if we were to find a vector from the point 1, 3 to 7, 5, I would take my x coordinates, 7, and I would subtract it from 1, where it ended from where it started, and that would be my I components, and then my j components, I would do 5 minus 3, giving us our vector v of 6i plus 2j. In bracket notation, 6, 2 with our pointy brackets. Now we're going to get to the stuff that's a little bit more like why is this in the chapter with polar coordinates? Now we're hitting some trick. How can we find a vector represented by magnitude and direction? So instead of thinking about points, we're thinking about it's going to give us the length and the angle. Kind of think our radius and our angle are polar points. It tells us what angle to go and how far to go out. That's going to be given to us right here. Our vector is going to be the magnitude times cosine of theta times the I component plus sine of theta times the j component. Why does cosine of theta multiply by I? Because cosine is the one that goes with x. And remember, I is the component that tells us left and right. And sine has been going with our y stuff. And j is the component that tells us to go up and down. So we're basically kind of turning this stuff into, I don't want to say like polar vectors, but it's giving us an idea of how long and what angles we're going instead of just giving a point where it ends. So we're going to take the vector -2, 2 square root of 3, and we're going to write it in this form represented with sines and cosines. So the first thing we have to do is find the magnitude of this vector. So we're going to do the square root of -2 squared plus 2 square root of 3 squared. -2 squared is 4. Here's where some of us have to be careful. I'm still seeing this mistake from a few people. 2 square root of 3 squared, you do this on your calculator, it needs to be in parentheses. Some of you are just squaring the square root 3. This would be 4 times 3, so this would be 12. If you type it in your calculator and you get 6, you're not doing parentheses. So that's square root of 16, which is 4. So we have that. That's our magnitude. Now we just need our angle. How are we going to find our angle? Well, let's think about where this vector is pointing. -2 negative 2 root 3 is over here. If we think about geometry and we think this is negative 2, this is 2 root 3, even our unit circle stuff, if we think about, maybe you're thinking inverse tangent or geometry, we're thinking special right triangles. This would be a 30-degree angle. This would be a 60-degree angle. This is a special right triangle. This is our 30, 60, 90. So the angle that takes us from our initial side, which is that like x-axis, over to where our vector is pointing is 120 degrees. So our vector in this new form would be 4 cosine of 120 degrees I plus 4 times sine of 120 degrees J. Certainly a little confusing, but we're just finding the angle that we're going to get there and how long the vector is. It's making us think polar wise. All right, example number 2, write the vector v in the form ai plus bj, given the magnitude of vector v is 3 and the angle it makes with the positive x-axis is 45 degrees. This is more commonly what you see with these types of problems. So we're just going to simply plug them into this formula that we have. So our vector written in ai plus bj form, we're going to take our magnitude, which we are told is 3, and we're going to multiply this by cosine of 45i plus sine of 45j. We know how to evaluate cosine of 45 degrees and sine of 45 degrees. That's our pi over 4. We're thinking unit circle. So this is 3 times the square root of 2 over 2i plus sine of 45 is the same thing, square root of 2 over 2j, giving us our vector 3 square root of 2 over 2i plus 3 square root of 2 over 2j. So this vector with the positive x-axis makes a 45-degree angle and is 3 units long. This next example, very similar to what we just did here. So if you'd like to try one on your own, that would be a good time to pause and try it. I'm going to go through it here in a second, but you can always pause and see if you get the answer that I'm getting. It's a little bit different because you might have to guess at what some of the values kind of transfer over to. All right, a ball is thrown with an initial speed of 25 miles per hour. That's actually going to be our magnitude. That's going to help us kind of find how long it's going to be, because you'll have this idea of this distance in a set amount of time. Boom. That's how far it'll go. And then we know the angle here. That makes an angle 30 degrees with the positive x-axis. So we have this right here. We have our 25 miles per hour sending us off in this direction with this 30-degree angle right here. Express this vector in terms of I and j. Well, we're going to use that formula above. V equals our magnitude. It's going to be 25, and then we're going to plug in 30 degrees into cosine and sine, to get our components. Cosine of 30, that's root 3 over 2. Sine of 30 degrees, that is 1/2. So we're going to multiply these by 25, and we get 25 square root of 3 over 2i plus 25 over 2j. What is the initial speed in the horizontal direction? Horizontal, that's our I direction. So that's 25 square root of 3 over 2, which if I typed in my calculator earlier, it's about 21.65 miles per hour. So it's going pretty quick outward. And then what's the initial speed in the vertical direction? We look at the j components. 25 over 2, that's something we can do in our heads. That's 12.5 miles per hour. So definitely not traveling as fast upwards as it is outwards. And that'll be our 9.4, kind of our introduction to vectors. One more video for us for 9.5 on the dot product coming up here.